In this video, we're going to be discussing how to find the real zeros of a polynomial function. In sections back, we were able to find real zeros if it was already in factored form. But what if you have a long polynomial and you need to find the zeros, meaning you have to factor it? But if it's of high degree, it's sometimes hard to factor something that has a degree of 4 or 5 or higher. So if we don't have the tools to be able to factor something that high, how do we find the zeros of the polynomial algebraically if it's not already factored? Well, there's a way to find the zeros, and it can sometimes be a little tedious, but it's the only way to do that, which is using the remainder theorem or factor theorem. As I described in the first section 5.1, we identified the real zeros of the polynomial function by factoring, or using the quadratic formula. But like I said, what if it cannot be factored easily, or if it's a polynomial of degree 3 or higher and we can't use the quadratic formula? A couple tips that we can do. First, let's recall what it means to divide. When we divide 14 by 4, that means 4 is being divided into 14. When we do division, let's recall how this works. 4 divides into 14 3 times, then I multiply, subtract, and find my remainder. So the divisor is the number that's dividing into. This is the dividend, which is the number underneath the division symbol. The quotient is the answer, and the remainder is 2. It's important to recognize what these terms are so we put things in the right spaces when we have larger polynomials. And remember, we can always check the division by writing the dividend as a sum. 4 times 3 plus the remainder will give us the dividend that we started with. So we're going to use these tools to solve bigger things that involve x's. So remember, dividend is always equal to divisor times the quotient plus the remainder. So let's use this for polynomials. Let's say we have a set of functions where g of x equals x minus c. Let's find f of x over g of x and f of c. And then let's notice any patterns that we might have. First, we're going to divide. We're going to divide f divided by g. So g is the divisor. So we're going to use this as the divisor on the outside. We're going to divide that into f, which is x squared plus 2x minus 4. So we're going to practice our long division. I know we did a little bit of this back a section or two ago when we were finding oblique asymptotes, but we're going to get some more practice in this section. So when we divide, we look for x and we divide that into x squared. I'm going to get x as a quotient. X times x is x squared. X times negative 1 is negative 1x. Then I subtract this whole value. When I subtract, the first terms go away, and then I just have 2 minus negative 1, which is 3x, and then I bring down the negative 4. Then I do it again. X divides into 3x 3 times. 3 times x is 3x. 3 times negative 1 is negative 3. Then I subtract this whole quantity. The first terms cancel. That's always what will happen. Then we have negative 4 minus negative 3. So that means plus 3. So I end up with a remainder of negative 1. So what this says is when you divide a polynomial by a factor, where to make this 0, x would be 1, that means f of 1, if I plug 1 into the function, I get 1 squared plus 2 times 1, we're plugging this into f, minus 4, and that equals negative 1. Did you notice something that happened there? Let's do it again. Let's take this f, and we're going to divide this g into this f. Let's do it again. X minus 4 is g, and we're going to divide that into x squared minus 3x minus 4. X divides into x squared x amount of times. X times x is x squared. X times negative 4 is negative 4x. When I minus this whole line, the first terms cancel. Negative 3 minus negative 4, that means plus 4, so I have a positive 1x, and bring down the minus 4. X divides into x one time. 1 times x is 1x. 1 times negative 4 is negative 4. So when I subtract everything in this line, the first terms cancel, and then negative 4 plus 4 is 0. So I get a remainder of 0. Now let's try to plug that same 4, which would have been giving this a 0. 4 minus 4 is 0. Let's try to plug 4 into the original function f. Let's see what happens. 4 squared minus 3 times 4 minus 4. 16 minus 12 is 4. Minus 4 is 0. Are you seeing a pattern? Let's try one more time. Again, let's divide g into f. X divides into 2x squared 2x times. When I multiply, I get 2x squared plus 4x. Let's subtract. First terms cancel. Negative 3x minus 4 is negative 7x. Bring down the 1. X divides into negative 7x, negative 7 times. So when I multiply, I get negative 7x minus 14. Then I subtract this whole quantity, which gives me 0 for the first term, and then 1 plus 14, which is a remainder of 15. Now, what makes this 0? Negative 2. What happens if we plug negative 2 into f? 2 times negative 2 squared minus 3 times negative 2 plus 1. Well, that's 3 times 4, which is 12. 12 plus 6 is 18. Sorry, that's wrong. 2 times 4 is 8. 8 plus 6 is 14. 14 plus 1 is 15. There we go. I knew that wasn't right. All right, so now you're going to notice a trend that is happening here. So what did you notice? These numbers match. These numbers match. These numbers match. Okay, so when you divide by x minus a number, the remainder is always going to be the same answer as if you just plugged this value into the function to begin with. This is a much faster way to find the remainder than doing the whole long division. So if I said, find the remainder of this division problem, it would be much faster just to do f of 4, and you get the remainder much faster than doing this long division. So what I noticed is that when you divide by x minus c, the remainder is always going to be f of c. Notice these guys are the same. And that's exactly what the remainder theorem down here is stating. It says if f is a polynomial function, then if f of x is divided by x minus some 0, then the remainder will be f of c. So let's use that, continuing on to the next page. So on the next page, we're going to start by finding the remainders. But we're not going to use long division. Let's just use the remainder theorem to find the remainders instead. So if I were to divide x plus 2 into this long polynomial, and I don't want to use long division because that takes too long, and frankly I don't have enough room here, all I can do is, if all I want is the remainder, I can just plug f of c into this function. First we have to determine what c is. C is what would make this thing turn 0. So c would be negative 2. And then if I plug that 0, potential 0, into the function, I get negative 2 cubed plus 3 times negative 2 squared plus 2 times negative 2 minus 1. And I'm going to have my calculator help me. So we've got negative 2 to the third power plus 3 times negative 2 squared plus 2 times negative 2 minus 1. So my remainder is negative 1. So even if I were to do the long division on a separate piece of paper, you're still going to get the same remainder, which means this factor does not divide into this polynomial perfectly. Perfectly would mean it would have a remainder of 0. So that means this is not a factor. Let's try another one. Over here, let's try x minus 1. If x minus 1 is a factor, then we're going to let c equal 1. It's what makes this factor come to be equal to 0. So that means this x would have to be 1. So I'm going to take 1 and I'm going to plug it into the original function. So we're going to have 1 cubed plus 3 times 1 plus 2 times 1 minus 1. That's 1 plus 3, which is 4. Plus 2 is 6, minus 1 is 5. So I have a remainder. Both of these gave me remainders that were not 0. So next comes the second theorem of what this section is about, the factor theorem. The factor theorem states that let f be some polynomial function like this one up here. Then x minus c is a factor of it if and only if f of c is 0. In other words, if there is no remainder, that means this factor divides into this polynomial perfectly, perfectly meaning there's no remainder. If there's a remainder, then it doesn't divide into it and it's not a factor. So the factor theorem actually consists of two parts. If f of c is 0, then that means x minus c is a factor. Vice versa, if x minus c is a factor, then f of c is 0. It goes both ways.